Hello and welcome to this session on emerging technologies. My name is Javier Ramirez, and as a developer advocate at Amazon Web Services, my mission is to give you as much information as I can about our services, so in case you decide to build your applications on top of AWS, you will know the best way to do it. If you have any questions after watching this talk, feel free to ping me on Twitter. My private messages are open and you have my Twitter on screen, supercoco9. Today, I'm going to be speaking about managed blockchain in the cloud and about ledger databases. And some of you maybe know about these things, but maybe some of you are asking, well, I kind of know what blockchain is, but I'm not sure about a ledger database. So even if you might not know the name, you might be familiar with the use case. So imagine you are an application developer and you have a database and you have the requirement that you need to keep track of all changes in the history of your tables. So if you're a developer and you have to implement this, what will you do? Well, I'm not saying I'm a good developer, but I will go to Stack Overflow, okay? And I went to Stack Overflow to check if people were having this kind of issue, and I found several people having this problem. And I found this quite old question, actually, asking about, hey, how do you version tables in SQL? And out of the answers, this was the accepted answer. And it provides two different solutions. One of them is actually quite cool. I've implemented in the past a few times when I had this kind of requirement. So the first answer is, well, since relational databases are not really built for this kind of a scenario, you need to create your own set of history tables, and you need to create somehow in your application a mechanism that every time there is a change, you are going to persist the old data into the history tables, you are going to update the current data with the new data, and then you have to implement some way on your applications to query the history, which sounds okay, but it sounds like a lot of work. And if I have many applications, I need to make sure they all use the same mechanism. And if I have many applications in different programming languages, it can be tricky, but it works and it's totally fine. The second option is maybe have a separate data warehouse. And I understand where this is coming from, but for many use cases, it might not be the best idea. But for some, it might be. But yeah, we have an answer, okay? And just not to be unfair, this answer is quite old. If you check this thread, there is a newer answer that says, hey, by the way, many relational databases today support the new SQL standard in which you have temporal tables that allow you to have versioning of the tables in a native way. And that's true. But those databases allow you to tamper with history. Some databases allow you to remove entries in some of the, in the history, and all of them allow you to drop the history. So if you need to audit all the changes, you cannot just rely on the temporal capacities of relational databases because you cannot verify that nothing was changed in the history. What is the solution then? Well, the solution is ledger databases, which is very related to blockchain. I'll tell you later how it's related. So a ledger database is just a database in which we can solve this use case. Every time there is a change, it's committed to something called an immutable journal that no one can change. So at any point, you can see the whole history and you can cryptographically verify that no one has changed the history. I'll do a demo later about that. And when it comes to ledger databases, we find two types of business scenarios. One in which you have centralized trust and one in which you have decentralized trust. What do I mean by this? Well, imagine you are the drivers and vehicle licensing agency in your country, and you want to keep track of every vehicle that is registered, every time the vehicle changes ownership and when it's deregistered, so you can know who is going to pay taxes for that vehicle. Or maybe you are in a highly regulated industry like healthcare and you want to make sure you keep track of your inventory and what has happened with this item of your equipment. So for that, you need to have a ledger database, but you are a central authority. You don't need to share your database with anyone else. There are a different case of business scenario, which is when you need to share your data with other entities. Imagine you are a consortium of financial entities and you're going to be transferring money with each other and you have transactions. Would you trust a single bank to have the database of the transactions? Well, if I were the other bank, I would feel a bit uncomfortable. It's like, I don't know, if you own the database, who is to tell me that you are not changing anything? So, it sounds, of course, banks are not going to do that, but, it's, you need to trust it, okay? So what banks and other companies, of course, any exchange has done in this case is basically they create some kind of central authority. So they create an authority in which all of them have a stake and they all participate and they implement sophisticated mechanisms for auditing. Or maybe they use some kind of escrow in which they also have like a third party in which they deposit their trust and they need to audit and so on and so forth. So each of those mechanisms is time consuming, is resource consuming. But of course, it's super interesting for the business to have a way of sharing the data. So is there a better way to have decentralized trust in a system? Well, that's exactly what blockchain is about. And that's why blockchain has been very hype in the last few years, because it allows you to have a scenario in which multiple companies can share data. They can independently verify the whole history of the data, and they don't need to depend on any central authority. So I'll tell you later how this works, but hopefully you can imagine how interesting this is, not only for financial institutions, but also, for example, for supply chain networks in which different actors want to make sure that they know exactly what happened to one particular item throughout their lifetime. Okay? And when it comes to blockchain, the layer database is just one part of the system. It's where the data is stored. We also need something called the consensus mechanism. I'll tell you about that later. And we also need something called the smart contracts, which is a way to run applications on top of the network. Again, I'll tell you about this later. But now that we already know a high level, overview of what is a ledger database and what is blockchain and the type of scenarios that they can solve, I'm going to tell you which services Amazon provides for ledger databases and for blockchain and how they work internally to verify that your data hasn't been tampered with. So Amazon Quantum Ledger Database, or QLDB for short, is just a central authority, central trust ledger database. Your application can write data to the database, can read data from the database, can access the history, and at any point we can verify that no one changed the history of the data. So the way it works, when your application is inserting, updating, or deleting data, we store the data in the journal, and that data it's cryptographically verifiable, and your application then has access to both the current state of the world and to the index history of the changes. And interestingly, the interaction is going to be with something very similar to SQL. So if you already know SQL, it's very easy to start working with Amazon QLDB. And also very interesting, we support ACID transactions, which is basically the same transactions guarantees that you are going to get in any relational database. So the changes to QLDB are atomic, are consistent, are isolated, and are durable. So you can rely your business logic into the database for those kind of things. Okay, so why did we choose to build a ledger database? I mean, we could have just built a library on top of DynamoDB or AuroraDB or some other database, but as I saw at the beginning, trying to build a ledger database with trust on top of an existing database is not really easy, and it's not going to give you capabilities like the verification of the data, so you can make sure that no one has been tampering with the data, and it's very easy to make mistakes on this. So we decided we couldn't use a generic database for the use case of a ledger database. And then we thought, okay, but maybe we can go with one of the already existing blockchain approaches. So if we use a blockchain, we already have the ledger there, but we chose to build our own database because blockchain has been designed for the use case of distribute trust. And when you don't need distribute trust, using a distributed network is a waste of resources. It's going to add unnecessary complexity, it's going to add latency, it's going to add cost to the system. So we decided building a ledger database with centralized trust was the right thing to do for these scenarios in which you need central trust and you need to have the guarantee that no one is tampering with your data. So how do we guarantee that the data is immutable? Well, we do it in two ways. The first one, which is quite simple, is like every time you send any change, we just append data to the journal. That's it. We never overwrite anything. So we update, and we don't give you any interface, any API, any way to change the history. That's about it. So since you don't have any way to change the history, you cannot change it. No more and no less. You can only append new data or append new transactions to the system. And but what if someone somehow managed to actually change the data in the system, because you have like a rogue actor and you manage somehow to change the data, even if there's no API for that? Well, here's where blockchain, it's used. When you use blockchain, the ledger database, the way the data is stored is like this. Every time there is a transaction, those transactions are stored in a block. A block might have multiple transactions, but you have one block. And in one block, we store the data, and we also store something called the hash for that block. The hash is a digital fingerprint generated with something called SHA-256. So this fingerprint is generated in a way in which I pass the data from the transaction, and I also pass the data from the previous block in the system. So I'm going to be passing data from the current block and from the previous blocks. And with that, I'm generating a fingerprint. A cool thing about SHA-256 is that if I generate a fingerprint for one object, and then I change a single bit of the data and I fingerprint again, the fingerprint is going to be completely different. So that means once I generate a fingerprint for one block of data, if anyone changes any data in that block, when I recalculate the fingerprint, it will be different. So I can check, hey, wait, this was my fingerprint, this is a new fingerprint, someone has changed some data here. But since we are using also the fingerprints from the previous blocks to calculate our fingerprint, if anyone is changing a single bit on any of the previous blocks, when we try to recalculate and compare the prints, we are going to see that they don't match. So we have a cryptographic way to actually verify that no one is tampering with the history of the data. So in this way, each block is chained to the next block, and that's why it's called a blockchain, because the way we store the data, it's guaranteeing that the data you have in one block is consistent with the whole history. And if anyone is changing history, we are going to mathematically, cryptographically be able to verify that history was changed. So QLDB, apart from being a ledger database, is quite cool because it's fully serverless. You don't have to worry about instances, type of instances, CPUs, memory, drive, storage, absolutely nothing. You just send your data and send your operations, and you pay for that. You pay for the storage you are using, and you pay for when you're doing writes or reads or network transfer, you pay for that. If you are not transferring any data, if you are not doing any operations, you only pay for the storage. And you don't have to worry about the scaling. You just do your queries, do your inserts, and we take care of scaling the workload. You don't have to worry about that. It's also highly available. Every time you store data in QLDB, we persist the data in 3 different availability zones. So you can be sure, even in the very, very, very infrequent event of an availability zone having trouble, you can still keep up and running with QLDB because it's highly available in the other two zones. So how does it work? How you interact with QLDB? Well, we created a superset of SQL, which is called particle. And so if you already know SQL, you already know particle. There are a few interesting bits. Of course, you can do joins if you want in QLDB. But since keeping track of history and doing joins can be a bit tricky, if you prefer, you can use nested data. So you can, if you want, store the data. If you have parent and child rows, you can store the child inside the parent row directly. So even if we behave like a relational database, behind the scenes, the storage we are using is not really based in rows, but based in documents. And this gives us flexibility for working with nested data. It also gives us the flexibility if in the future you decide to change the schema of one of your tables, that's okay. Because since we are not based on rows, we are based on documents, even if you change the schema of one of your tables in the future, you can still query the old data and the new data, and we are not going to have any issues. But basically, the bottom line here is you interact with SQL, which is, you already know SQL, you already know how it works. Before we continue, I want to do a demo of QLDB in action. For this demo, here it is, my browser. I have the web console of AWS, and I'm going to search here for QLDB. I have a ledger database, which is called vehicle registration, and I want to run some queries. And it's very convenient because you have a web interface for that. Of course, you will do this usually in code, and I will show you now how to do this in Python, but it's convenient to be able to do it here. So we have some tables here, and we have like some information about the tables. So I want to see everything that is on the vehicle registration table. Okay? So this gives me, as you will expect, the information about the table, as in any other database. As you can see here, we have a nested data here. The primary owner and the secondary owners are nested data, and that's fine. So that's nothing, that's just a query. But if I want, I can actually query the history of this vehicle. Of this table. And here I have the history. I have here the block information, I have here the hash for the block, and I have here the data. And I want to show this in a slightly nicer way, so let me just show you here for a second. So I'm going to check the history of a particular vehicle, so it's easier to see what we are doing. So here we are saying, okay, for this particular vehicle, version 0 was on this date, version 1 was on this date, version 2 was on this date, okay? And if I want to check together the metadata and the data of the transaction to see the changes, of course, I can also do that. And here I have the metadata from the transactions, from the history, and the information about the data on the table at that point. So I can see on the first version, I have this primary owner. On the second version, I change the ID of the primary owner. And in the second version, I add an ID for the secondary owners. So that's basically what I have here. And since this is a relational database, of course, I can do joins, and the joins behave as you will expect. Here, I'm joining the person data with the driver's license data, with the vehicle registration data, and I have here information about the three different tables as you will expect. So as you can see, interacting with both the data and the history is kind of easy. But I want to show you something a bit more interesting. I want to show you same thing for Python, and also how to verify transactions. So this is Python code. I only have to import the driver for QLDB, and I can run queries as the one you see here. So if I execute this code, we should see that we get the output. So this is Python, and these are the vehicles matching this condition. That's fine. Then, of course, I can do also update operations. In this case, I'm going to select a driver, select person from the from the database, and then I'm going to be updating the valid to date from the driver license. So let's execute this. So you can see we can also update data, of course, not only select data, and here it is. And of course, I can query the history. So in the same way that you saw me querying the history on the web interface, I can query the history from Python. So let me just show you here a query history query. Okay, so these things work. But the interesting bit, the one I wanted to show you here, is about verifying the transactions. So I have here a piece of Python that is going to do the following. First, we are going to go to the database and we are going to query a particular record from the database. Once we have this particular record from the database, we are going to generate the fingerprint. We are going to check, hey, for this particular record, give me the digest, give me the data, the fingerprint, yeah, the digest for this record. Now I'm going to store that record locally. Okay, so I store that record in Python. And then I'm going to change one bit on that digest. And I'm going to query again the database, and I'm going to say, generate again the digest of what is on the database. And I'm going to compare both of them. And I'm going to see that actually they don't match. So I can know that someone has been tampering with the data. In this case, we haven't been tampering, of course, with the data on the database, but we have been tampering with the digest, and we have a different result. So let me just execute this, and we'll see what's doing. So first, it's just calling the database, and we are generating the digest, and we are comparing the digest with the status of the database, and it's going to say it matches. Then we are going to flip a bit on the on the digest, and we are going to compare again, and it's going to tell me, oh, it doesn't match anymore. So let me here, I have the output, querying the registration, the document is verified. Now we are flipping one bit in the document, you can see on the selection, and we are going to see if it's not verified. And actually, we see that the document, we correctly see the document has failed to verify. So why is this important? Because you could sign a contract and send to the signer of the contract as proof the digest. And then each of them could tell you in the future, hey, I have this digest for my contract. Can you validate that I signed this? And if they pass you the digest of the contract, you go against the database and you are going to see that actually that's legit. If another person tries to verify that, but they change the digest because they want to fool you, they want to tell you, oh, you know what, I didn't sign this, and they paste you a different digest, we can tell them, well, actually, we have verified that in our database, what you are passing me doesn't match. So we cannot accept that as a signature. You see what I'm doing here, yeah? What we are doing is verifying cryptographically that the information on the database works. And this is super important for many people. For example, BMW decided to build a use case around this. They wanted to verify that all the vehicles of the BMW vehicles could be audited through the lifetime. For example, every time you change insurance provider, or even every time you have an accident, when you go to the mechanical workshop, so if the car changed ownership, even the mileage of the car, all those things they wanted to keep track of. And they choose to create something called the BMW Digital Passport application, which is using QLDB for centralized trust. So other companies are trusting BMW, and they send them their data whenever they are servicing a car or whenever they are changing the insurance. BMW is actively getting data from those companies, and that data is stored in QLDB. So as an owner of your car, you can keep track of everything that happened throughout the history of the car. But enough about centralized trust. I still want to speak about the centralized transactions in the last few minutes I have for the presentation. So we already saw the centralized transaction is when you have a consortium of companies and they all want to have a way to share the same data and verify independently the transaction history and making sure no one is tampering with that history. And for that, we want to avoid having escrow or a central authority that is going to be expensive to maintain. So blockchain allows you to build trust in a network of nodes. And the way it does it is by having a ledger database, which is not centralized but distributed. Every actor in the system, every node in the system is going to keep a full copy of the database locally. So they can all verify the whole history of transactions, and the database is synchronized all the time across different actors. So how does it work? Well, there needs to be a consensus mechanism, and different blockchains use different type of consensus. But basically, every time an actor wants to change data, it needs to propose the data to the network. The network needs to agree. Once they reach an agreement, they persist the data in all the ledgers, in all the nodes in the database. So a single node cannot independently change the data because the network wouldn't accept it, so the other networks will realize that data is not valid. We also have smart contracts, which are applications that can run on top of the blockchain network, and depending on the network, they can be written in different languages, but basically they can interact with data in the ledger database and in other databases, and they can run distributedly on the blockchain network. So they are blockchain network today, and they are super cool, but as distributed systems, they are hard to manage. So we decide to offer Amazon Managed Blockchain, which is no more and no less than a blockchain which is compatible with the open source blockchains like Hyperledger Fabric and Ethereum, but it's fully managed by Amazon. So you don't have to worry about creating the server yourself. We do it for you. You can start in just minutes a full network. We support today 2 different frameworks. We hopefully will be supporting more frameworks in the future. It's decentralized. No one owns the network. And since it's using AWS technologies, it's very cost efficient and well integrated with the rest of the ecosystem. So the way it works, you create a network. You invite other accounts in AWS to join the network. If they accept, they can start adding nodes to the network. Then you can start adding applications, and then you can start operating. And we offer both Hyperledger Fabric and Ethereum. Ethereum is maybe the most well-known kind of blockchain in which everything happens in the public. Anybody can join the network, and there is full transparency of all the operations. This sounds super cool for some kind of organizations. For other organizations, Hyperledger Fabric, it might be more interesting. Hyperledger Fabric is a permission network in which you need to have permission. Someone needs to invite you to the network, and they allow you to audit everything that happens in the network, but also they allow private transactions between 2 parties in the system. So it's very interesting for many type of businesses that want to have a central database, but also the possibility to work independently. And no one owns the network. You create a network and you invite people, and each one is going to have a copy of the database. The moment someone joins a network, they are part of the network, and even if the original owner disappears, the network is still alive. And each member is paying only for what they are using. So each member is paying for the nodes that they have in the system. Each member is paying for the data they are writing, and each member is paying for the storage they are using. But no one is paying extra for having the network up and running. Since we are running on AWS for all the nodes in the network from different accounts, we can have some optimizations. For example, we are using QLDB as the underlying ledger database, so we can offer guarantees, and we also can use our own certificate authority. So we are more efficient and more performant than other blockchains that you will find outside of AWS. And of course, we have today already many customers using our managed blockchain solutions. That's what I have for you. If you want to explore blockchain on AWS, You can visit the Partner Discovery Zone to see partners that can help you start the journey. And as I told you at the beginning, if you have any questions, just let me know. Thank you very much and have a good day.